So there's constantly another function of k. Then you need to find this from here. Once you have this, you do the partial derivatives this one, then you can find this one and finally. So I just give a hint. Okay, and just remind what we discussed in the last class. We want to see how the effect of the infinitesimal canonical transformation for Hamiltonian. The Hamiltonian, what happened in Hamiltonian is different for the other function. First, we know under the infinitesimal canonical transformation, the canonical variables transform from T0, this old one, and go to the new one. So when the canonical variable transform, then the Hamiltonian at T0 and at T is different. It follows the follow here. This is a condition for the canonical transformation, right? So that means if we change, since the Hamiltonian, it just show that this Hamiltonian speed gave us this Hamilton's equation motion. So at this case, in correspond to this side of canonical variable, the Hamiltonian gave this equation motion. Then at the other side, when you do the canonical transformation, you need a new form of Hamiltonian, and this new Hamiltonian give the canonical variable follow this. So that is different from other case. Then we are going to look is the change of Hamiltonian from here to here, but this is not this difference, because when this change from this here to here, the canonical variable will change. So that is the difference between the final and the initial, which is, since the change, you have to go to another phase, right? And this phase follow the canonical transformation is has this one. So by substituting this one into here, we obtain this one, right? That is end of last class. And we are going to discuss the connection between this symmetry and the conserved quantities. So what that means, we are going to look at this one. Let's try to understand the physics here, right? This means the change of Hamiltonian. So change Hamiltonian, this change, right? So this change is associated with the infinitesimal canonical transformation. So kind of transformation that then leads to the change of Hamiltonian. This one is dynamics of the generator G, right? What is generator? This generator for infinitesimal canonical transformation. So here, from here to here, actually is this generator play the role transfer, right? So this play the role, and this dynamic total time derivative will associate with this change of the Hamiltonian under the canonical infinitesimal canonical transformation. So this one is symmetry, right? Whether a change or not, this reflect the symmetry of the system. So that gives us information, and then this one, if zero, that is conserved. So that is the relation between the symmetry and conserved quantity. Symmetry here, and whether the quantity is conserved or not. Symmetry, whether it's symmetric or invariant or not. That is directly related to this. So let's do example. Okay, just it. If is zero, invariant, right? That is invariant under canonical transformation. Then immediately get this total time derivative for generator equal to 0 from here. So that means G is conserved. So that is the conclusion. Now we are going to see what kind of canonical transformation and or what kind of symmetry that the system has, and associates or implied give us what kind of physical quantity is conserved. So with this relation, now let's do some discussion, right? First, suppose if G, okay. Let me first give you the idea. We are going to see here. So we know G is the generator of infinitesimal kinetic transformation. This transformation will transfer this eta to zeta, right? That is what happens. And the associated with change, we have associated with epsilon, which is the associated change parameter. This parameter is associated with transformation, right? And so AK is transformation. And then we are going to see after this. So what happened here, right? Symmetry or environment. Let's see, just environment. Environment or not. Then conserve or not. So that is the story here. Because as we say that the generator will different type of generator will generate different type of the canonical transformation. Then associated with the canonical transformation we have a parameter. One kind of parameter. Then with this transformation we are looking for the Hamiltonian. Our system, if the system Hamiltonian is changed, it will lead to the total time derivative of this generator. If not changed, invariant, then immediately let's say this generator is conserved. So this generator is what kind of physical quantity? Well, that is we are going to see. So then let's do some examples here. Example 1, if the generator is one of the canonical conjugate momentum, right? That is if this one. Then we are going to see under this generator what kind of transformation happened, what kind of parameter associated with, and if this is invariant, what kind of conservation, right? So in this case, let's see how to change, right? Because we know this infinitesimal change of this canonical variable is following this relation, right? We discussed before. It's determined by the Poisson bracket. So let's see, for general coordinates, let's say delta Qj is epsilon. This must be same, right? The Qj and G is the Pi, Pi, right? Poisson bracket. If generator momentum. If generator's momentum, then let's look at what the generator general coordinates here. So according to the Poisson bracket, when J equal to I is 1, right? So that means is this. Then you can see the right hand side is the displacement. Right hand side, epsilon. So epsilon has a dimension of displacement, right? That will give this answer second question. What happened? So if this generator is a momentum, linear momentum, then what happened is it changed the displacement by amount, infinitesimal amount of epsilon. Okay, how about this momentum? We do the same thing, but not equal to 0, right? So no change. Okay, I just leave here. So you see here, if we select one of these linear momentum as a generator, what happened? Along this S direction, the general coordinates or displacement along that, and others also does not change, right? If J not equal to I, also unchanged. and all the momentum unchanged. So that is what happened for this up here, and we know this parameter is displacement. So now, okay, so we have this. So then is okay. Then we know the partial h equal to negative displacement, right? So q is qi, right? Because it's epsilon is qi, right? There it is. D pi dt, right? From here. Epsilon is the displacement and g is linear momentum. So that means this change or dynamics of linear momentum, pi is linear momentum, it will change the Hamiltonian. So the Hamiltonian change only controlled by this, no any others, right? So if that means is in volume under the displacement is qi. So is symmetric, right? Under translation. Then the translation. And then dpi dt equal to 0. So linear momentum is conserved. That is this analysis from here. So immediately we know that is relation between the Hamiltonian, the symmetry of this Hamiltonian, and this physical quantity, which is the generator. So you know the generator actually is physical, one of the physical quantities. So now is example 1. Example 2, if the generator is a displacement, what happens? What kind of parameter epsilon is, and what the associated physical quantity is conserved. So now if G is minus QI, I use negative. Okay. All right. So again, we use this delta eta equal to epsilon eta G is epsilon eta minus QI, right? That's first the general coordinate, that's B epsilon QJ minus QI, that's equal to 0. So no change on the displacement if the generator's displacement. How about this? P delta PI epsilon PG delta PG, sorry, minus QI closing bracket, that gives us okay. QI PG is 1. So PG is minus 1, but minus meant plus, right? So here it's still plus. And then you can compare with this dimension. Dimension of epsilon is momentum, linear momentum here, right? So with this, okay, so compare with the same now. That is linear momentum. Then we are going to look this. So change of the Hamiltonian under this displacement of or translation of momentum, not the position, is equal to is follow this. So what happened is, if there's a displacement Qi time dependent, then definitely system will have a change. And this change is associated with this linear momentum. Right? That is this relation. So if it's 0 means this is H is invariant under this momentum transformation or translation transformation. Then we immediately know that this displacement is constant. It will not change. That's it. Let's do more. Oh, you are here, Renata. Okay. How about the angular momentum? Right, we use the momentum and the position. How about the angular momentum? So now let's see. Number 3. So if G is angular momentum, suppose let's select LZ. Just select one of these rotation. Angular momentum about this z-axis. Okay. Z-axis is x I p I y minus y I p I x, right? Let's suppose this is not the case. Okay. Then now let's see, this is a rotation line. So now let's do this infinitesimal change of this canonical variable under this generator. Now here I use instead of I use this Poisson bracket, but you can use Poisson bracket for each one, but I can also use, because these are equivalent, right? I use this one. So that is epsilon partial LZ, since I use G is LZ, right? Partial, you see this is just refer to P1x, right? Epsilon partial LZ partial Pnx and minus epsilon partial LZ partial x1 minus epsilon partial LZ partial xn. Or q, let's use q instead. Otherwise, as just P1 Pn, right? Q1. I'll compute this x and y, Q1. And that's B equal to delta Q1, delta Qn, delta P1, delta Pn, right? The infinitesimal change of canonical variable. Okay, from here we have this, since there, so we have this, let's do that. Partial is partial P1, partial is partial P1, P1 here is, okay, now we have this one. Delta xi, if select the delta qj, which is xi, so that is equal to epsilon partial lz partial pix, right? Back-Hartree relation. Okay. Then let's look this one. So if I partial lz partial pix is minus actually minus yi. Yeah. Right? And if yi is epsilon partial lz partial piy, which is minus epsilon piy, no minus. This minus here. Remember this epsilon xi. Delta pix is minus, right? So minus partial lz partial xi, that is minus epsilon. So partial xi is piy. Then delta piy is minus epsilon partial lz partial yi. Partial yi is minus epsilon, or minus plus, right? Here we have minus, here also minus, so plus epsilon pix. So That means from this infinitesimal canonical transmission, we found the relation. If this generator is angular moment along the z-axis, we have the relation between this infinitesimal change of canonical variables with the itself, right? So now what does it mean? First, we need to find, as I say here, this kind of infinitesimal canonical transmission, we need to see associated with this chain. What is the parameter? So in this case, let's look at this one. Partial H, because this, right, the relation. So if this equation means this dimension on left hand side equal dimension on right hand side, right? So the dimension of, let's look at the dimension. Left hand side is energy, right? And that is some epsilon, and then this dimension is angular momentum. Divided by time. Now, left hand side is okay. So now let's keep epsilon. We do not dimension of epsilon. We're going to determine. Angular momentum is energy times time, right? Dimension. And divided time. So you see this cancel. Then that means the dimension epsilon is dimensionless. And next up, we are going to prove what is the angle. Okay, so here we analyze first this kind of a generator will generate this change of the canonical variables, like follow this relation, and we are going to see this relation actually associates with the rotation. And this parameters the angle. So now let's confirm epsilon and what kind of the type of the infinitesimal. Let's look at this. Look, this is we look this kind of rotation which we familiar along the. Let's look rotation about z-axis. Okay, so rotation about the z-axis here like this, right? This is a z-axis, and we have a rotation. That is rotation of here. This is r, and this is r plus delta r, right? And then I'm going to use color. So here, this one is delta r, right? That is what happens if we rotate about the z-axis. So now, let's define angle here. That is delta phi. So you can see here the delta r is, okay, now I'm also introduce n hat, which along the z-axis. So we have this, move to this. Okay, so that is, you see, if I use a cross product, n hat cross product go from n hat go to r is given to delta r, right? So that is n hat cross r. And angle, right? We have to associate with the angle. So the delta r direction defined by this cross product, and the magnitude is, this magnitude is r. The r itself, this with the angle, right, is delta phi. So this case, I prefer use this matrix, and then I deal with the cross product. So I, J, A, and n is 0, 0, 1, and r, x, y, z, right? So you will see that gives us this after rotation, each x, y, z components will change. So you see here for the I, the direction is this one multiplied by this one, so minus y, right? Minus y delta phi I direction. And j is remove this j column and this negative. So negative, okay. So here this is a 1x, right? Yes. Yeah, this is a minus. But here this is also minus x, but we have a minus in front, so that is plus x delta 5 j and 0 k, right? Because no, if it's remove k, so that is 0 term. So this is a delta x I plus delta y j plus delta z k, right? Okay. Same. This is for r. If we consider this rotation for this vector r. Similarly, for the momentum, you can do the same thing. Delta p is n cross n hat cross p delta phi. And that's also equal to, I'm going to use px, py, pz. Same thing, so here that is minus py delta phi plus px delta phi j and plus 0 k, which is be correspond to delta px py delta pz. Okay, from this you can have this conclusion. So a change of this kinetic variable, both the coordinates and the momentum, that correspond to change of delta q1, delta qn, delta p1, delta pn is equal to all the term has a delta phi, right? Take outside, and inside is partial LZ, partial P1, partial LZ, partial Pn, minus partial LZ, partial Q1, minus partial LZ, partial Qn. Because you can see they are same, right? You can see here, x, y. So this is minus yi, here minus y. And then this x, this x. So only difference here, we have epsilon, here is delta phi. So epsilon, that's equal to delta phi, which is dimensionless, is angle. Angle, yeah, that's all. It's angle. So now we have this idea is if the generator is the angular momentum, the associated infinitesimal kinetical transformation is rotation. And this rotation parameter is angle. So if, again we have here, now here, G, sorry, not photo. T is minus delta phi, which is angle, dLz dt. So in 0, that is invariant under rotation. Under rotation, this is a performance or translation about z-axis. Then the angular momentum about the axis is conserved. Conclusion. So now you can, I think I will play one more. Then you have the idea how the different generator will generate different type of the infinitesimal canonical transformation. Then associated that transformation is a kind of symmetry of system. And okay, I'm going to extend. Here I just select OZ, right? In general, G can be any along this any here this along Z, you can along any arbitrary is this N and the rotation about this, right? About L. About the Ln. Same thing. Right? So this case, if in general that is a generator, whatever generator it is, but if it is associated with the angular momentum project to an arbitrary direction axis, then we have the same thing. So the only difference, the same thing means this epsilon is definitely angle, then the canonical variables will change associated with that. You just follow this relation, and you can obtain how much change. Then look this Hamiltonian. If Hamiltonian conserved has a symmetry with respect to this, then it is conserved. Right? It's angular momentum about this direction, projected this direction is conserved, and the Hamiltonian has a symmetry rotation about this axis. So now we have number 3 and number 4. Now let's see if generator is Hamiltonian itself. So if it's itself, what is epsilon? What kind of a canonical transformation associated with this? Let's look. Because the change of the infinitesimal change of the canonical variables is epsilon eta G, right? And in this case, G is Hamiltonian. Okay. Remember this? You can remember the total time derivative is evolution motion. Total time derivative variable is controlled by this Poisson bracket. That's partial. Remember this? Right. So here, this is 0, right? For this, the canonical variable does not depend on time explicitly. So here, immediately you got this. Or D T. This is just remind. So what is this parameter epsilon? Associated with this canonical transformation, if the generator is Hamiltonian, look at the dimension. So if this is a eta, this is eta, it's be same, so this be T, right? Time. So which is time. So that means Hamiltonian. Any kind of a canonical transformation is generated Hamiltonian. That transformation is nothing but the associated change of time, right? Because it's a time associated with the transformation. The canonical variables from T0 to T. So that is what happens. And if you find the canonical variable change with time, you must definitely immediately know that generator should be Hamiltonian. Okay. So in this case, then now let's again here, right? So we can minus dH dt. So if that is where if we say symmetry that if H is invariant, does not change with time under time, then it is constant. It makes sense, right? It is constant, so H is conserved. And that makes sense. We know Hamiltonian, the system does not depend on time. The Hamiltonian is constant. It is conserved. So those are examples to see the relation between the generator, infinitesimal canonical transformation generator, and the Hamiltonian. and the symmetry of system. So that is connection. So far we discussed this infinitesimal canonical transformation. Now we go to the finite. How to extend our discussion from infinitesimal canonical transformation to the finite canonical transformation? Now we are going to discuss or consider this way. Actually, it's very simple. The next topic is finite. Transformation. So now, infinitesimal canonical transformation. So now let's consider in the phase space, initially a TA and then TB, right? So we have a transformation here. Okay, in the phase space theta. So we have this in this A and this B, right, position. So that is a active chain or active view, right? We can see here in the same phase, but we see this function will change in the value, right? So that is a change. Okay. So now what we are going to say that the canonic transformation, I'm just make simple. Actually, it's nothing but we can have I from 1 to infinite, infinitesimal canonical transformation, right? So if we divided this finite canonical transformation by infinitesimal difference, right? So now, if that means if we want to see the effect of canonical transformation is nothing but the sum of all the succession of this infinitesimal canonical transformation. So that is the idea. Okay, and then we correspond to we introduce parameter. We correspond parameter like epsilon for the infinitesimal canonical transmission. Parameter for canonical transmission, we introduce alpha. So if we say alpha, that means that any variable is a function of alpha, right? Or any function is function of alpha, depending on how alpha, the length, how much it is. So if we divide this d alpha is infinitesimal change. Then what will happen is that we do this infinitesimal change and the sum of all accumulate together until the finally, so that is when this U naught is when alpha equals 0 is, right? And any from A to B, the B is dependent on length, how much finite. Then we have this relation. Then we divided alpha by d alpha is infinitesimal change. That is correspond to the infinitesimal change canonical transformation. So if we use this and actually U is continuous. It is no any doubt, right? Continuous as alpha. So what happens is we know the U is start from here, and then if we keep continue on the path from the infinitesimal canonical transformation together, sum all together, then go to the finite. So at any position, the U be continue with R, with alpha. And that is try to find the relation between the canonical finite and the infinite transformation. So with this idea, then let's consider for the infinitesimal canonical transformation d alpha, right? That is. Then we already know this change observable. This is in the active, right? Active view. u. We just see in the same place, but we see the value change of this function. This change by Taylor expansion, sorry, okay, the infinitesimal change, we know that is very direct. That is this relationship, right? Okay. Then from here, I replace epsilon by d alpha, and u g here. So we have this in infinitesimal. Then we have du with alpha. I just divided d alpha both sides. That is nothing but by controlled by this Poisson bracket. See, the Poisson bracket is very important. Okay. So this is the infinitesimal. Now for finite, canonical transformation, we use the Taylor expansion. Okay, so Taylor expansion u is a function of alpha. We start from this u naught, which alpha equal to 0, plus the first order derivative is alpha to the first order du d alpha when the alpha equal to 0, plus second order alpha equal to 0 and plus higher order, right? That is the Taylor expansion. We're going to use this. Okay. So now for this one, first du d alpha when alpha equal to 0 is okay. I'm going to use 0 is this Poisson bracket when alpha equal to 0. So that is from here, right? Okay, from here that is, and then now let's look at the second order, since now we are going to find the relation here. This increased order, second order d square u d alpha square is equal to d alpha du d alpha, right? And then the d alpha du d alpha is u g, right? Is this if I define this one as a v, the Poisson bracket of u and g is another function v, so that is a d alpha, right? And again, here whatever u and v, so this is their function, so that should give us Poisson bracket v and g. And then v itself is the Poisson bracket of u and g. So this is second order derivative. Then do the same thing. So similar for the others, right? So now we have so now u alpha is u naught plus alpha u g 0 plus alpha square 2 factorial u g 0 and plus alpha q, sorry, the first order. Yeah, this is the first order. Yes. First order, second order. U G 0. So we have the formula. This is the formula for any function at the finite canonical transmission, how to obtain this the finite canonical transmission from the infinitesimal canonical transmission. We just play, you see this rho by the Poisson bracket. again. That's why we introduce portion bracket, since this is very important. Okay, this is a general formula. Now let's discuss or play some examples to have an idea about this. Okay. Examples. First one. Let's say U equal to zeta G. And so U naught is eta G, is the beginning, right? No question, okay. So now let's see if the U is nothing but the new canonical variables. G is U canonical variables. And U naught is from here, right? When alpha equal to 0, which is original. And original is all the canonical variables, okay? So if this case, now let's look. The new canonical variables for the finite canonical transformation follow that formula. That's equal to eta G plus alpha zeta G and alpha equal to 0 plus alpha square 2 factorial zeta G and G and 0 and alpha Q 3 factorial zeta G 0 and others. Okay, so this is a general formula, but depend on what kind of a generator, then we can do the details, right? So here I didn't give the generator, then we cannot do the details. Now, assume, or if, let's just say, if the generator is angular momentum, what happened? You know that is rotation, right? So if G is LZ, then what is epsilon? Alpha. This is alpha expanded, right? That means alpha speed angle, I'm going to say that, right? Immediately we already know. We already discussed before, right? So associated with this generator, if the angular momentum, then associated with the change of the infinite type or its parameter canonical transformation is angle. So now I put here. Okay. So now let's consider only the x components, right? I consider I is xi at time t, and eta I is xi at t naught, which is lower xi. I use capital is the new one, and the lower is the initial. Okay, so now G is capital X I P I Y minus capital Y I P I X. Now let's see if we are going to find this Poisson bracket, right? So now let's look at this one. Because let's look first. X I capital, right? This capital X I G equal to X I L Z, right? G is L Z. And L Z is here, right? So that is X I L Z is X I P I Y minus Y I P I X. Let me use capital. And we're familiar with the Poisson bracket. So here, okay. So that is xi with the first one, xi p I y minus xi between bracket y I p I x. And here we know Poisson bracket xi with x at 0, right? Xi with piy also 0, right? So now only the non-zero is here. Xy with yi still 0, right? Xi with pix. That is 1, right? Minus 1. Minus, okay. Minus, but here, when you do this, y is outside, right? because this is a product. So when you do that, the y is being here, and then x I p I x, right? So that is this one. So the first closing bracket is x to this argument is y. Then the second one, so here, x, I, g, g, right? We are going to look second one, is this one. And this one is, first, this one is minus yi, right? Here. And g is x, I, p, I, y, minus y, I, p, I, x. Then again, if you take minus I here, this is a y, I, x, I, p, I, y, plus y. Yeah, minus plus, right? Y, I, y, I, sorry, x. So here, this is 1, 0, this is 0. Only non-zero is this term, right? Y, I, and here. So then here, I gave you this y, I, p, I, y is 1. So that is minus x. Let's see. Oh, okay, it's minus x. Okay, so you can do the same thing. You will see here. The first one is y, and second go to x. The third one you will see go back to y. So that is alternated. So now let's summarize here. Okay, I haven't given the 0, right? This is just any, this eta. If eta equals 0, so x, I, L, Z, 0 is minus y, I, 0, which is minus y, I, right? Lowercase. And then here, y, I, L, Z, 0, which is minus x, plus x, I, this is x, lowercase. This is a capital. Same thing, right? So then we have finally x, I equal to, here. xi is the finite canonical transformation with finite alpha, that is xi, that equal to the initial eta I or eta j, which is lowercase xi, right? And the second one is, this one is alpha is angle, right? Theta. Oh, we have a minus right here. Minus y, lowercase yi, theta. And minus, because here this is a minus, right? So it's minus xi theta square factorial, and then this plus y theta cube 3 factorial. This third up to xi whole power. So if you select xi outside this term, xi, then you have a 1 minus factorial and plus, right? Plus. And then I take the y minus yi outside, so I have a theta, and then plus, minus take outside, so this is minus. Minus theta cube. 3 factorial. So you know this infinite series is cosine sine, right? So this xi cosine theta minus 1i sine theta. And you know this. We know about the z-axis, when we do the rotation, the xy change with this angle, right? So now you can see we just stop on here. Let's see if I have time. Yes, very good. So now let's do one more exercise. That is example 1, right? Okay, example 2. example 2, now we consider G is H Hamiltonian. And so we know alpha equal to T, right? That is for sure. And again, we use U, let me see, U still select X. We still select X. Here. H, now we select H is one dimension motion, particle under this. This is one dimension motion. Kind of one dimension. So we define this. So now let's see what happens. This kind of canonical transmission with a generator Hamiltonian. And we know definitely that is time evolution or change in time, so that's speed dynamics of X in terms of time, right? So now let's use this relation here. U, okay. U alpha, so now U alpha to T, right? So UT is U naught T equal to 0 plus alpha is T now, there is T here, right? So there's U H naught plus T square 2 factorial U H and F. We're going to use this relation here, right? So now we need to find this, right? We need to calculate this Poisson bracket. Then we have this Poisson bracket, so we can have this. We have this formula. Okay, so now first, since we select U is X, so now let's look at this X. Since one dimension, I don't need the index, right? It's just one X H. Okay. X H is P squared over 2 minus MAX. Then the Poisson bracket, we know X will commute with P. Not commute, I mean, sorry, caught my head. That's the Poisson bracket that with P and with X. So let me just do one more. Minus X MAX. That's constant, right? So this is 0. And the Poisson bracket 0. So now let's look at this first term. First term, I take constant outside. So this is P squared. P squared, this is X P is P plus P X P, right? Two terms. So X P is 1, so we have a 2. 2P, and then the factor 2 is P over N. All right, so that is the first order, first the Poisson bracket. Now let's look at the second. One more. The Poisson bracket. So now, here, because we already obtained this Poisson bracket of X is H is a P over M. And Hamiltonian is P squared 2M minus MAX. Then we know there are also two terms, 2 Poisson bracket minus PMAX. The first one is 0 because this is the same Poisson bracket 0. So the next one is minus MAPX. PX is minus 1, right? Because we change order. So minus 9 becomes 1. Well, sorry, I have an M, right? I forgot this M. So then there's M cancel. There's 8. Okay, how about this one? The third one. This one we already know, that is 8. And you know, actually I just immediately write down 0 degree because it's constant. Any Poisson bracket, I mean this any variable or function with constant is always 0, right? So now we have the means that it truncate to the server, right? So that means this is not series, it became to the finite. Now let's see what this looks like. Okay, so now x actually is at any time, right? X naught. Repeat again, so that is first order x h naught plus second order x h h 0 plus third order x naught is lower x. Old one, right? I use lower x. The first one plus t, and then the first commutator, Poisson bracket is p over n. Then that is capital P, but when they take 0 is lower p, right? Lower p. Then second one is t squared over 2. Then here we have a, right? Over a. And 0. Others. So I think if I use, okay. So maybe I use x naught initial, right? The initial position, initial momentum. So that is x naught initial position plus here p naught OM is p naught, right? Is you familiar? Constant acceleration, right? But we didn't use Newton's second law. We used this analytical mechanics, and we got this beautiful result, similar things. So once, just remember this. This gives us, when you want to do this atomic derivative, generator must be Hamiltonian, right? Okay. Let's do one, I think not one. You can also do one more, but yeah, I will not discuss a new topic today since, or we can, let me quickly and we can stop. You can go back to prepare a holiday. So numbers 2, 3, right? Again, number 3 in this case, again, now still use Hamiltonian. But a different type of Hamiltonian. So if G is H is a harmonic oscillator, simple harmonic oscillator. Okay. Now we are going to find this, right? So we are going to find U. T is U naught plus T U H naught plus T squared. Okay. Example, if U is, again, we use X, right? One dimension harmonic oscillator. So we have X, anytime T is X naught plus T X Hamiltonian, T squared 2 factorial, X Hamiltonian. Okay. Now we're going to do this. Let's see this. Just keep this one. And then finally, you can substitute this. Then measure T. Not bad. X P squared 4N plus X squared. So again, very easily this one is 0, only this one. So that is 2N X P squared, and the normal is second one. X, H, H. That is the first one we already know that that's P or M. P squared or 2M plus X squared. And this one 0, so only this one, so we have 2mk p x squared. Then we have xp, so that's minus, right? And twice, so we have minus mk. Oh, sorry, we have x. Then keep the third one, x, h, h, h is minus k over m x p squared 2m plus. Here, this one is 0, so we have only these two. It's minus 2m squared k x p squared. Here we have 2p. So minus 2 to cancel, m squared k p. And do the same thing, let me just, since then we are going to summarize, so this one almost. Is here minus k m squared p squared 2m plus k over 2x squared. And again, only this one is non-zero. So you have a minus 2m squared k squared. And then this p x squared is minus, it became plus. So m squared k squared x. Sorry, p. Oh yeah, x, yes. Okay, so then you can see the alternate. The first one is p, second one is x, third one p again. So that is alternated. And then finally you will find this solution. So this is endless, right? You cannot truncate. And then the reason because the potential is not linear. It is x squared is not x, so that makes this into the final. So final xt is x naught plus t over n minus t to the q over n squared k and plus t to the fifth power n to the this is squared k squared minus t 7 and 4k we take out p, that is for p x, then plus minus t squared over m k plus t to the fourth power m squared k squared minus t to the sixth power m q q and x. So finally you can sum all x naught. I take this t outside, so I have a summation n from 0 to the infinite minus 1 to the nth power n to the n kn t2n that multiply tp, and then plus another summation is n from 0 to the infinite n plus 1 minus 1 n plus 1 k n plus 1 t2n t squared x. Okay. I want to, if I give you any generator, I think now you can follow this, and the key is to try to find this Poisson bracket, find the relation, then you can get this dynamics. If it's a term, it's dynamics, right? If not a term, for example, angle is a kind of a canonical transformation, finite canonical transformation. What happened is a function or variable associated with this. All right, so I'm thinking, since we still have another 2 class in after the Thanksgiving, I might cover a little bit about the end of the chapter 9 about the vector Poisson bracket. That is, and then I go to chapter 10. That's very good. We have this chapter 10. This cover the first idea about this how to make the canonical transmission from the old one to the new one has cycling. Then we are going to solve the problem. That is our goal, right? Okay, good, good. I know you have a homework. Hopefully this not too much time occupy your holiday.
Finish.
Sorry?
Hopefully we will finish in the vacation. Homework.
Oh,
Will you have homework?
yeah. So due is next Tuesday, right? Yeah. The content is next Wednesday, so you probably, because I want to grade it for you.
Yeah.
Then next Thursday is the last day. I'm going to deliver the final exam, take it home. You are prepared the final exam. So today is made clear, right? That in the here now everything is good. But during that we need to prove everything, so that makes the mind is the mind made it mad. But I hope now you have. Yes.
Double check with you about the final exam, you'll cover which chapter?
Okay. Chapter 3, 8, 9, and 10. Maybe just section 1 or 2. It's see how much we can cover. Yeah. So take it home this final exam. At home is December 1st, and in class is 8th, right? And so that is 50%. This is another 50%. So, for example, maybe have a 3 problem you take home and another 3 in class, and cover by this. Open textbook, open notes, open homework in the class. You just take all the material you think that help you, and we will work on this in class. Yes. This okay. From here to what is this one? This one thing? That is 0, right? Is this 0?
Operating doesn't raise the state.
Okay, actually it's n, right? This operator is n. So n in 0 is 0.
And 0 is 0.
Because that is quantum, you see here. N, right? That is the corresponding eigenvalue. This one is 0, right? But then you have 0 and is 0, right? So must be 0.
Eigenvalue is 0.
Eigenvalue is 0, right? Because this corresponds to the eigenstate. This is also a harmonic oscillator, right?
Yeah, but
I know, but then you are going to see here. You want to,
yeah.
but here is already 0, right?
Yeah, but
You cannot lower than that.
but I tried to operate a dagger on first bra.
This one, right?
Yeah.
Remember, that is for the A. Right? So that's 0, right? That makes sense?
So we can't raise the state by operating a dagger?
Yeah, you can do this way, but it's 0, not 1. You write down 1. I thought you write down 1, right?
It doesn't raise the state in bra.
Yeah, you can, this A dagger apply this bra, right?
Yeah.
Is what you want to say. And equal to 1. That is not correct, as I say. right? Because, yeah, you just know A dagger after this is equal to the, this is A after that is already 0 and the left dagger is still 0.
Thank you.
Okay. But A dagger applied cat, yes, that is right. Right. Right is just opposite. Since we are not the commission. Okay, good.
Okay.
Enjoy your Thanksgiving.
Okay.
See you after.
Oh, I didn't bring myself at school.
Yourself?
Yeah.
Oh. Oh yeah, I would have to be.
You don't have class?
No.
Oh, okay.
She canceled it today.
Sorry. I still keep the class with no any reason.
Okay. You can say, have a nice weekend and happy Thanksgiving.
How is it?
Yeah.
Looks like hero.
There's some of bread, or you can, if you want to take some of cookie or some of food there.
We already.
Okay.
You already? Oh, okay.
Yes, we have to come to the
We came in the.
Early,
Bye.
right.
Dr. Hammond,
Yes.
the class goes on until it's stopped by some outside force.
Say again?
Your class goes on until it's affected by some outside force.
All right, happy Thanksgiving.
It's a